All right, thanks. And our last speaker for this session is Hannelore MacDonald from ETH Zurich. Thank you.
Thank you. Is my mic on? Okay. Yeah, so today I'm going to be talking to you about some of the work I've been doing for my postdoc on how host heterogeneity can select for parasites that drive increased transmission dispersion. And this project is all theoretical, but I'm very interested in if anyone has data or an experimental system that could be used to test into this theory, I'd be really interested in hearing about that. Okay, so sorry, where are my notes? Never mind. Transmission in many disease systems is often highly dispersed, where a few cases are driving most new cases in that epidemic. For example, for a typical outbreak of measles, around 20% of cases are driving 80% of new cases. And more broadly, we see this pattern where transmission is highly dispersed in that a minority of cases are driving the majority of new infections. And this is thought to be driven by host heterogeneity. So how this works is that in this heterogeneous host population, for example, on the right, where we have this heterogeneous host population, the circles are hosts. The circles with the thicker outline are higher yield from the perspective of the parasite, and that they will be driving more infections than the thinner circles. So as a disease is spreading through this population, if it eventually gets to this higher yield host, it can really take off. So in this way, heterogeneous host populations can drive increased transmission dispersion. And this heterogeneity can come from a couple of different factors. For example, this high yield host could just be more gregarious. It has more contacts so that it has more opportunities to spread that infection once it's infected. Other sources of heterogeneity could be some biological heterogeneity, where some hosts just maintain higher parasite loads so that when they're just more infectious, so that when they have that opportunity to transmit, they're more likely to do so. And a lot of the work on transmission dispersion is focusing on these host factors that are thought to be driving this high transmission dispersion. I'm asking a slightly different question, which is whether host heterogeneity can select for parasites that drive increased transmission dispersion. So given that there is this underlying heterogeneity in host populations, can host heterogeneity also act indirectly to select for parasites that drive enhanced transmission dispersion? So how this could work is that perhaps the parasite could be specializing on these higher yield hosts, and this could then be a mechanism that drives increased transmission dispersion. So to get at this question, I developed a mathematical model where I'm considering I have a simple case where I'm just considering two different host types. I have a high yield host that does not transmit as much when it's infected because it has a low transmission rate, and it's not infectious for very long because it's experiencing high virulence. And on the other hand, I have a high yield host that has a high transmission rate, and it's more tolerant of the infection, so it's experiencing lower virulence, it's infectious for a longer period of time. How this works in the model is that transmission and virulence are both functions of the within host growth rate of the parasite. And this within host growth rate is what is going to be evolving from the parasite side, so changing over time. So both virulence and transmission increase as the within host growth rate increases. And the low yield host always has lower transmission than the high yield host. And the low yield host also always has higher virulence than the the high yield host. Okay, so in this model, I've adapted my modeling framework from this really nice paper by Day and Gandon, where I'm explicitly considering the evolutionary and epidemiological dynamics of this system. So the number of infected and susceptible hosts in these two types are changing over time. That's the epidemiological side of this. And this is impacting selection on the within host parasite growth rate. So selection pressures are changing as number of hosts available changes. This impacts the evolutionary dynamics, and the evolutionary dynamics then feed back and impact the epidemiological dynamics, because this within host parasite growth rate is controlling both transmission and virulence of those infected hosts. Okay, so right away we can make this prediction that high yield hosts are probably going to select for higher within host parasite growth rates than low yield hosts, because that cost of transmission, or The cost of virulence is a bit lower in these higher yield hosts, so we expect it's going to select for higher within host parasite growth rates. The parasite can get away with that in this host type. While in the low yield host, that cost of virulence is a bit higher, so we expect it's going to select for lower within host parasite growth rates. And we also have this expectation that there is, in a way, a trade-off in this model between specializing on the two host types, because you, if there's selection to specialize on that high yield host, that parasite is going to end up with a really high level of virulence in the low yield host. Okay, so in this model, parasite fitness is being measured as the effective reproductive ratio of that parasite, and this is being split by, because both hosts can contribute to infections, this is being split by the average number of infections coming from both host types. And then transmission dispersion is measured as the variance to mean ratio of RE. This is capturing the variation in transmission or in parasite fitness coming from those two different host types, depending on how much they contribute to the total fitness of the parasite. Okay, so I have this model again where I'm explicitly considering both epidemiological and evolutionary dynamics. The math behind this is that I've got a simple SIR model controlling the epidemiological dynamics, and I'm using a version of the price equation to express the evolutionary dynamics, where this epsilon bar is the average trait value of the within host growth rate that's changing over time, proportional to this covariance term between the within host growth rate and parasite fitness. So if that covariance term is positive, larger and larger within host growth rates will be selected for. If it's smaller, if it's negative, smaller trait values are selected for. And you see this example in the bottom where if that covariance term is positive, there's positive selection on the within host growth rate because larger trait values are giving that parasite higher fitness. So that's just how, it's the math behind all this. Okay, so my question then is, again, how can parasite fitness drive increased transmission dispersion? I'm going to be showing you some plots that show how this variance to mean ratio of RE, or what I'm defining as transmission dispersion, is changing over time as the epidemiological and evolutionary dynamics are changing as well. Okay, so first prediction of the model is that transmission dispersion is very high early in an epidemic. This plot is showing transmission dispersion over time with and without parasite evolution. And you see that the model is predicting that with parasite evolution, this can drive higher transmission dispersion compared to a case without any adaptation. So what's going on here is that early in an epidemic, there's susceptible hosts are there's a lot of susceptible hosts around. And this then selects for high within host parasite growth rates. So this plot on the top is showing susceptible hosts over time with and without evolution. The plot on the bottom is showing the within host growth rate of the parasite over time, where that blue line is showing selection that's occurring in the high yield host, and the green line is showing selection in the low yield host. And what you see is that early in an epidemic, when susceptible host density is very high, there's strong selection for a large within host growth rate because it's adapted for the parasite to really be exploiting those available hosts. And this then drives high transmission dispersion because that high yield host is transmitting more than the low yield host. Because you see that both high yield and low yield hosts, they both have those high within host growth rates. And the high yield host has higher transmission and lower virulence, so it's driving more transmission. Okay, the model also predicts that transmission dispersion can be maintained at equilibrium when that parasite's evolving. So this, again, is showing transmission dispersion over time with and without parasite adaptation, but in this case now we have later time points where the dynamics have started to settle to their endemic equilibrium. So what's going on here is that at later time points we have more moderate host densities, and this then selects for lower within host parasite growth rates because now there's more weakened selection for high transmission rates, and the impact of that cost of virulence starts to come in, and it drives lower within host growth rates. Okay, and then these more moderate within host parasite growth rates are still able to maintain some transmission dispersion. And you see that its transmission dispersion is predicted to be higher in this case where we have parasite adaptation versus no adaptation. Okay, the model also predicts that increased transmission dispersion evolves when most hosts in the population are low yield. So this plot here is showing transmission dispersion at equilibrium versus the percent of low yield hosts in the population, again, with and without evolution, for a case where parasite fitness is much higher in the high yield host versus the low yield host. And what you see is, right around when there's about 80% low yield hosts in the population, This selects for parasites that are driving especially high transmission dispersion because high yield hosts are responsible for a lot of that infections that are occurring. Okay, finally, the model predicts that large differences in host quality drive high transmission dispersion. So this plot here is again showing transmission dispersion at equilibrium versus the percent of low yield hosts in the population. And what's going to be changing is low yield host virulence. So in the beginning, when high yield and low yield hosts have the same level of virulence, you see that selection actually drives decreased transmission dispersion. But as virulence increases in that low yield host, the model predicts that drives higher, that selects for parasites that are driving higher transmission dispersion. All right, so in conclusion, this model is predicting that populations with few high yield hosts can select for parasites that drive high transmission dispersion, and that large differences in host quality can select for high transmission dispersion parasites. And with that, I'd like to thank the theoretical biology group at ETH, especially my two advisors, Sebastian and Roland, as well as my funding from the NSF. And again, I put my email there. If anyone has ideas on how we could actually test this theory, I'd be really interested in that. Thank you.
We have some questions. Coffee is coming up, I promise.
Yeah, that was interesting. Over here.
Hi.
Could you talk a bit more about the assumptions underpinning performance in the two hosts? I think you touched on it and I missed it. And I think those are pretty crucial.
Yeah, so how heterogeneity is working in here is just those two trade-off functions in the beginning, where the high yield host has higher transmission. The high yield host either has higher transmission, can have higher transmission and or lower virulence, and the low yield host has lower transmission and or lower virulence. Thanks.
Thank you. That was a very interesting talk. But I may be missing something, and I apologize if I did. But so are you assuming that the virus has sort of phenotypically plastic growth rate, so that that the same virus in two different hosts will grow at different rates?
No, it's the same. Yeah, same virus or pathogen, and the selection's being driven in those two host types. So it's adapting on the both simultaneously.
So then I was confused, because as you showed some plots that shows as time goes forward, the growth rates in the two different kinds of hosts don't follow the same path.
Yeah, sorry, I probably said that too fast. That's just showing the selection pressures coming from those two hosts. And there's an average trait value that I should have shown that is what is spreading in the population then.
Oh, I see.
Yeah,
Thank you.
sorry about that.
Excellent. So can we thank Hannelore?
Okay.